Hi, I'm Quillen, and I am going to be talking with you about some calculus today. My current plan is to make this a series of videos going all the way through the AP Calculus BC curriculum. The AP Calculus BC curriculum follows a college Calculus 1 and 2 course series, or if you go to a school that uses a quarter system, it may be Calculus 1, 2, and 3. If your Calculus 3 is multivariate calculus, or if it has linear algebra as a component, then your Calculus 3 will not be covered in this series of videos. So, that being said, this can also be used for courses that are not specifically labeled Calculus BC or Calculus 1, 2, or 1, 2, 3. This will cover all of the topics discussed in Calculus AB, most differential calculus courses, and most integral calculus courses, although the integral calculus at the time that you're viewing this may not be up yet, as it will be towards the end of the series. Today, we're just going to talk about the requisite functions that you should really have a pretty good grasp on before you start thinking about calculus, before you start diving into limits and derivatives. And those important functions that we're going to be talking about today are, sorry about that. Those important functions that you should be pretty comfortable working with are your polynomials, your exponentials, your rationals, the whole trig family of functions. The arc functions are slightly different. The square root family of functions, and I will mention momentarily what I mean by family of functions. The absolute value function, and the floor and ceiling functions. Now, these are roughly arranged in order of importance throughout the course. These first four are probably interchangeable in how important they will be. They are all paramount. So if you don't have a great understanding of all four of these function families, please go watch another set of videos or read some to familiarize yourself with these. Hopefully at some point I will have made videos covering all four of these function families. The square root function you will likely develop some more familiarity with throughout the course before it is absolutely paramount that you work with it very cleanly. Absolute value is more comprehensible logically, in my opinion, and the floor and ceiling functions are really only helpful in applying concepts, and while they are not necessary for mastery in this course, they are really helpful, I think, especially later on when we start talking about Riemann sums. So I'm going to move over to Desmos, and we can start talking through some examples of each of these function families. So I have prepared 30-ish, 35-ish total functions that we're going to go through and discuss sort of what makes them tick, if that makes sense. So the most basic function is y equals c, where c is a constant. We're going to call that y equals 1 today. It's just, whoopsie, that's not what I meant to do. It is just one moment. Sorry about that. I misunderstood how Desmos worked. Let's try again. The most basic function, absolutely, is y equals c, where c is some constant. Let's call that constant 1, y equals 1. It is just a horizontal line. Now, this is a polynomial because x, the independent variable, is being raised to a power 0. And that gives you 1. Now, take this line and rotate it. You get y equals x. Y equals x is the most basic polynomial that people really think about as a polynomial. It is the linear equation, the most basic linear equation. And some important functions are that its slope is 1. So the coefficient right here, multiplying the x, is 1. And you can calculate that by noticing that as it travels vertically, it travels the same distance horizontally. You probably covered that in your Algebra 1 class. It also has a y-intercept at the point 0. And that can be changed if you add a constant to it. For example, 3. Its intercept is now at 3. The next very basic polynomial that you probably learned was y equals x squared. Now, just like x, it has an intercept at 0 that can be moved if you add a constant to it. So x squared plus 3's intercept is at 3. However, it, if you notice, has a changing slope. Right at the start, when it goes up by 1, it also goes horizontally by 1. But then after that, if you notice, it goes up by 3, and it only goes over 1 in that time, which means right in here, its average slope is about 1. But then right in here, this area, its average slope is about 3. That's a very interesting fact that you need to tuck away in your brain. Just notice that the slope changes over time. Now, you can also change the rate at which the slope changes by multiplying it by a constant. Let's remove that 3 so we can look at more of the parabola. But you noticed that the intercept was at 3 even though we were multiplying that x. So right here, it travels 1/2 and 1/2. So its slope is is about 1 over a much shorter interval. And then as it travels another half over, it goes up by 3/2. So its slope seems to be changing at double the rate, which is very interesting, and you should take note of that. The next one that you may have covered specifically, and possibly the last one, is y equals x to the third. Again, its intercept is at 0, and again, its slope is changing. But if you notice, its slope is always going up, and its slope is changing at a faster rate. If you look at y equals x squared, it opens more. It goes up a little slower. It takes longer for most points. It takes more x to get to that y than it does for the green line. Now, the important thing about polynomials is that you can combine them. And it will have everything that you add will have some influence. So the most dominant part, so the most influential part, is the x with the largest, greatest exponent. So this x is being raised to the third, and so it looks more like the y equals x to the third graph than it does any of the others. But this x squared part right here is making it so that it wibble wobbles and it has a greater breadth in that section right here, where before it just kind of got flat for a second. And then this 6x, you'll notice if I take it out, it also makes that wibble wobble bigger. So the x squared part makes the wibble wobble appear, and you'll notice if I delete it, it moves around. But the wibble wobble also got just a little bit smaller. So the main function of this linear component is increasing the wibble wobble. This x squared component does increase that wibble wobble, and that's not the technical term for it, of course, but that's a great way to think about it. But more than that, it moves where that is. So again, if I take it out, its center is closer to 0 than when it's present. And then this lonely 1 by itself just means that its intercept is at 1, instead of, if we take it away, it being at 0. So let's move on to our exponentials. And again, I'm going through very briefly with these, but you should have a pretty good understanding already. This is just ideally a refresher. So y equals 1 to the x. You might think that's the simplest exponential function, but if you look at it, it's not really exponential, is it? It's just the graph of y equals 1. And that's because 1 to any power is 1. 1 to any real power, that is just going to be 1. The true most basic graph of an exponential function is the graph of y equals e to the x. But e is a weird number that takes some time to think about if you don't already know what it is. So let's start with y equals 2 to the x. It looks very similar. As you can see, it almost looks the same until it gets into the land of the positive x. And you'll notice it looks like at around -6, it's just a horizontal line. But if you zoom way in, you'll actually notice it doesn't get to 0. Like, even at -7, where we thought it was already at 0, it's still above 0 by just the tiniest bit. And actually, you'll notice that you'll find that it never quite gets to 0. It asymptotes at y equals 0. Now, over here, it looks like it just goes up and up and up forever, never quite passing x equals 4. But that's not the case, really. It does go up and up and up forever, and it does get faster as it goes up. Its slope changes, but it doesn't asymptote ever. It goes to x equals infinity if you give it until y equals infinity to get there. And you will notice that when x equals 1, y equals 2. So let's use some things that we learned from there to talk about y equals e to the x. You'll notice it still goes to 0, and it still goes up and up and up forever. I know you can't check that it's forever, but trust me, it does go up forever. And you can, if you think about raising any number, and e is just a number, to an infinitely high x power, then obviously your y is going to be infinitely high. But let's think about what e is. So if you remember with 2 to the x, when x equaled 1, y equaled 2. So applying that to this, when x equals 1, y is going to equal e on this green line. And you'll notice that that is about 2.75 maybe. And if I just come down here and type e, it is 2.72 about. And this is just an observed fact. You will learn later on in this course what e specifically means if you don't already know from your Algebra 2 or maybe pre-calc course. So, what if we then do something to just the x on its own? What if we subtract 1 from the x? Well, let's leave that green line up and look. When this green line is at y equals 1, it's at 0. But this purple line at y equals 1 is at 1. And you'll notice that you'll actually find, if you look further in, that for every point the green line passes, the purple line also passes it when x is 1 greater. So you can then kind of deduce that subtracting from this x translates the whole graph this direction towards the positive direction. So horizontal translation, you work with just the x portion, and you may be able to find that intuitively, but it's important to know that it is in the opposite direction that you might expect looking at the operator, this minus sign. What then if you multiply the base, but you don't raise that base? Well, you don't really translate it because it looks a little too parallel, right? And it's one group, and so, excuse me, I'm sorry. But what you will find is that at every single point, the blue line is twice the green, or the red line is twice the green line. And that makes sense. If you double something, then it is going to be doubled unless you do something to that 2 that's doubling it. But what if you do something to the 2 that's doubling it? Well, it sort of gets squeezed in, right? It gets squished. So this means this function right here, the quantity 2e raised to the x, is actually a combined version of a different function. So this isn't really in simplest form. Another way to represent this is the function y equals 2 to the x times e to the x. And you'll notice that if I take away the red line, it does exactly follow that blue line. So you're multiplying two functions together to get this. And that's why it doesn't exactly give you what you might expect. Moving on to rational functions. A rational function is where you have a fraction with your x in the denominator. And you can be doing stuff to your x. It doesn't have to just be a number over x. The simplest one is, of course, 1 over x. And it has this iconic star shape where you're sort of missing the completion of the star. It looks like a lens flare. And if you have 1 over x, and I'm just going to go ahead and edit this a little bit, and negative 1 over x, it completes that lens flare star. So the important thing to note about this is that it actually does asymptote both vertically and horizontally. It has a vertical asymptote at y equals 0, at x equals 0 rather, and a horizontal asymptote at y equals 0. And that remains the same if you double it. It just gets there slower. It bulges a little bit further out. And you'll notice that if I do the opposite of this purple, I still get that same lens flare star look, but it is bulgier, like you would expect. Now, what if we start doing stuff to that x in the bottom? Well, 1 over x squared looks like this. You have this. It's just vertical, and if you think about it, that makes sense. You'll never have x squared being a negative number, so it can never be negative, right? So your doing stuff to the x will change. Raising x to a power will change which side of the x-axis it's on. But compare it to 1 over standard x, it's actually less bulgy. It takes a lot less time to get really close to that horizontal axis. What then if we mess with adding stuff to that x? You'll notice that it translates it horizontally. And just like with your exponentials, it's in the opposite direction that you'd probably expect. So y equals x plus 1, a positive shift, a positive addition, shifts the graph in the negative direction. So just remember in your brain that those shifts are still opposite what you would expect. Now, multiplying that x by a constant coefficient will decrease the bulge without flipping it. And it is the exact multiplicative opposite of multiplying the numerator by that same thing. So if we do 2 over 2x, you'll notice it's actually exactly the same as 1 over x. And you know that makes sense. The 2's simplify, cancel, so you're left with just 1 over x. What if you do both, though? So what if you combine a multiplication with a power? Well, you're on top just like you would expect. Let me change color so that it's easier to see. Do orange. So it's easier to see. It's all positive because it's being squared, but it's also less bulgy because it's being multiplied. But it's even less bulgy than either 1 over x squared or 1 over 2x on its own. And that's because you're combining those two. This is, again, multiple functions being done at the same time to this x. Let's talk about trig now. Trig is my favorite. Trig is my favorite by far. And we're not going to spend as much time talking about the y's because you really need to have a strong geometric base to understand this, and you need to know your unit circle, and I just don't have time to go over all of that. So, sine looks like this. Notice that it crosses through the origin. Cosine looks like this. Notice that it has an intercept at 1 and that it is half pi. It's half pi. You probably can't tell exactly from this graph, but you can estimate. It is at all times half a pi less horizontally than sine. Tangent is the ratio between sine and cosine, sine over cosine. And it is these strippity lines. A very important thing to notice is that it asymptotes many times. So just like these repeat every 2 pi, this also asymptotes every 2 pi. The exact value will change as you move it around and the period of that. So I said it asymptoted every 2 pi. That value will change as you do things to the function. Secant looks a little bit like just the top half of tangent mirrored. It's not exactly that, of course, but it sort of forms this tangent hugs the secant function. And if you look at secant and cosine, the secant function and the cosine function sort of kiss every half a period. And you will find, if you look into it, that they are actually exactly the same value at the center of each of their crests and troughs. The same is the case with the cosecant. It again hugs the tangent function if you shift it around. It actually hugs the cotangent function, mirrored to how secant hugs the tangent function. It's probably a little hard to tell. And the cotangent function, or the cosecant function rather, kisses the sine function. I'll make that a different color so that you can more easily tell what's going on. They get right, and they are exactly the same value at the center of their crests and troughs. Now, these next ones, they are a little bit less interesting for now, so I'm just going to show them. I'm not going to talk very much about them. Sine of negative 1x, if you went with this forever, it would look just like if you took the sine function and rotated it 90 degrees. But because you can't do that, because then it wouldn't be a function, and therefore setting it equal to y would be impossible, you just have 1/2 of a period of it, because that is as much as you can get without it crossing itself if you do the vertical line test. Same is true of inverse cosine. You'll notice that I'm using the arc notation. I tried to use them sort of evenly. Again, it's just half of a period of that function. Arctan is, believe it or not, still just, I believe this is a full period because tangent works a little bit differently. But you can imagine if you took all of those tangent lines and rotated them 90 degrees, you'd have a whole bunch of these little squiggly friends. And the only reason that it doesn't look like there's that many now is because then it would fail the vertical line test and therefore not be truly mappable by just setting equal to y. Secant, it's the same story, but you have this cool cut that becomes interesting when you start talking about limits. Same is true with cosecant. I made a typo down here. And then your arc cotangent is the mirror of the arctangent. And again, it's just a period. It's not the whole graph because that wouldn't be possible and it still being a true function. Now these miscellaneous ones, I really only have one super important thing, two super important things to mention. So let's first get floor and ceiling out of the way. Floor, if you don't know, takes the value of the argument, so whatever's in these parentheses, and finds the greatest integer less than or equal to it. So that's why it looks kind of like stairs. Ceiling does the same thing, but it finds the greatest, the least integer, smallest, closest to negative infinity, that is greater than or equal to it. Or, yes. And so when you put them together, you get these stairs that overlap. So ceiling will always be one greater than floor if their arguments are x. And if you square them, then the stairs sort of shrink. But still, ceiling is one greater than floor at all times. Next, let's talk about the square root. You'll learn more about radical functions as you start working with them, but the most basic one is the square root of x. And it looks like this. The only really super duper important thing that you need to know about square root x is that it is the exact same as x to the 1/2. As I'm turning x to the 1/2 on and off, the line is the exact same. It's just changing color. Now, the absolute value of x, perhaps it's really intuitive that you just take the graph of x and take the part that's below the x-axis and mirror it so that it's above. And that's going to be the case with anything inside of those straight brackets. So x squared, it's the same because it never goes below 0. But if you subtract something from it like that, then that part that would be below becomes mirrored and goes above. So it sort of looks a little bit like the bottom of the Batman logo, if that makes any sense. To illustrate this a little bit more, I have this somewhat complicated polynomial, both inside and outside of those straight brackets. And you'll notice that once it crosses, it follows exactly that line of the purple, but the part that's below is mirrored so that the distance below the axis for this is above the axis on the purple line. And that will conclude our video for today. I hope that you found this useful or that you enjoyed it, and I hope also that I will see you again next time. This is Quillen signing off.